Go ahead.
Okay, so thanks everyone for joining the HAO colloquium. Today's speaker is Dr. Stephen Kepler, and he's an assistant professor at Clemson University currently. His research focuses on the observational and data analysis studies of auroral and high latitude electrodynamics and ionospheric effects on high frequency radio wave propagation. He uses instrument primarily, including the sounding rockets, Incoherent scatter radar, and HF ionospheric sounding techniques to address these questions. And he received his PhD in physics from the University of Iowa under Dr. Craig Clensing, and previous to Clemson University, he was a postdoctoral fellow and research engineer at SRI International. And he received his BS in physics from University of Wisconsin at Madison. And today he'll present on the empirical auroral conductance relations derived from incoherent scatter radar and all-sky imagers. So go ahead whenever you're ready.
All right. Well, thank you. Thank you so much for inviting me and this opportunity to give this colloquium talk today. So, yeah, like I said, I'm going to talk about, this is a recent paper that's been published. It was accepted and published in the last couple months in JGR Space Physics. So I'm going to go through and present kind of a perspective of auroral conductance, what the problems are, at least one of the problems I'm attempting to address, and then kind of walk through some of the main results from this this particular paper. So again, the main focus is to look at the aurora, which you can see here, and then using incoherent scatter radar, which you can see right over here, or hopefully see. This is a picture courtesy of Craig Heinzelman, who many of you probably know. So let me go through and give a little bit of a background and kind of motivation. And I'll start off talking a little bit about high latitude electrodynamics. The polar region is an important area where we have a convergence of magnetic fields, and that the magnetosphere drives electric fields, and these electric fields map down along the geomagnetic fields down to the high latitude ionosphere. And these fields are all connected. In the ionosphere, there are currents that flow down along the magnetic field, which we call field-aligned currents, and most people know about those. But these currents have to close within the ionosphere, and ion-neutral collisions enable currents to basically flow across the geomagnetic field. And the basic, to follow the current continuity equation, you have this connection between the upward and downward field-aligned currents, represented here by current density. And these are related to gradients in the Hall and Pedersen conductivities, and also gradients in the electric fields as well. So the Hall and Pedersen currents form, again, which close the upward and downward field-aligned currents. The Pedersen current is parallel to the perpendicular electric field, and the Hall current is perpendicular to the perpendicular electric field. And both of those together form a total current, which is able to flow again across the geomagnetic field. In this frame, also, the other contribution that's very important are the neutral winds. So the neutral winds do modify, or we generally tend to use the frame of the neutral winds when we're discussing the electric field. And the final contribution, although I've mentioned this, is actually the conductivities, and that's represented here by sigma H and sigma P in this particular diagram. And one way I think about this is that these are sort of the electrical resistors in your circuit, and they kind of regulate how well these currents actually flow. And what I have represented here are the so-called conductances, which are the field-aligned integrated conductivity. So integrating along the geomagnetic field, you get conductances, which I'm going to be talking about and using that term, as opposed to conductivity, which is the altitude resolved profile instead. So this is kind of the big picture in terms of what at least what the focus is, and then the conductivities are the more specific thing that I focus on in this presentation. This is a little bit of an alternative diagram, but I feel a reasonably good block diagram that kind of describes the interconnection of the magnetosphere and how it couples with the ionosphere. And I understand too that, there are effects that go back from the ionosphere back into the magnetosphere, but my perspective is generally tend to be more of a top-down approach. So magnetosphere currents, plasma, and electric fields, which connect to ionospheric currents, conductivity, and electric fields. And then you have these blue boxes here, which sort of correspond to the agents of magnetosphere-ionosphere coupling. So the magnetospheric currents are coupled with the field-aligned currents, which couple to the ionospheric, the perpendicular ionospheric currents. The field-aligned currents, particle electrons carry the field-aligned currents, particularly in auroral phenomena. The electrons are carrying the upward field-aligned currents. So that's how those are connected, but you also get this particle precipitation, and these energetic particles that form the aurora that we typically see cause enhancements of the ionospheric conductivity. And then we can have that the magnetospheric electric field will map along equipotential contours to the ionospheric electric field. And so, as I mentioned, the ionospheric currents, conductivity, and electric field are all connected through Ohm's law within the ionosphere, which specifies how currents can close perpendicular to the magnetic field to close the magnetosphere-ionosphere current loop. And again, this is all in the frame of the neutral winds, in the frame of the thermosphere. So we have to take those effects into account as well. Although, for the purposes of this presentation, I'm not really going to be talking about neutral winds a whole lot. So I want to dive a little bit more into how we specify the ionospheric conductivity and give a couple of basic definitions, and then start to talk a little bit about some of the literature that motivates some of the investigation. So as I mentioned, there are these two fundamental currents, the Pedersen current and the Hall current, and there are two different conductivities that are associated with them. You can derive these values from using the two-fluid model. But effectively, you have the Pedersen current, which is all these are proportional to the altitude resolved electron density. Nu IN is the ion neutral collision frequency, and then omega IN is the ion cyclotron frequency. And we also have the electron neutral collision frequency and electron cyclotron frequency as well. So we have both of these terms for the Pedersen conductivity, and then also for the Hall conductivity. There's a slightly different form. In both of these cases, the dominant drivers for conductivities at high latitudes, there's two primary sources that are of interest. There's solar EUV, which controls the daytime. So that's basically what forms the E region during the daytime, is you have X-rays or EUV, which basically come down and ionize they're absorbed mostly in the E region. They ionize, there's a recombination process that causes an electron density enhancement. And because the conductivity is directly related to the electron density, you get a conductivity enhancement as well. The other source, which is the one that I'm going to focus on in this presentation, is particle precipitation. And this is, one of the a less certain source of conductivity, or understanding its effects are still something that we're studying these days. And it's actually a fairly active topic. But the basic idea is that auroral processes, particularly discrete aurora, diffuse aurora, pulsating aurora, which are kind of the dominant categories, there's different mechanisms in, say, discrete aurora that accelerate electrons up to keV energy ranges. So 1 to 10 keV is pretty typical for discrete aurora. 3 to 30 keV or so is pretty typical for pulsating aurora. Different acceleration mechanism. But the upshot is that you have these energetic particles that come into the atmosphere at about 1 to 30 keV. And these cause ionization enhancements to occur in the E region and the D region. So, roughly around 180 kilometers up to 150 kilometers. And as a consequence, you can sort of drastically change the circuit response and the electrical response of the circuit, because you're suddenly sort of tuning that resistor, or changing the resistor all of a sudden, or allowing more current to basically flow through the conductivity. So just to give a little more detail about exactly what kind of enhancements we have. So what I've showed here is a little bit of an example of some Pfizer data. And this just shows the electron density profile. So this was collected during at some interval in March of 2013. And what's plotted here, this is the daytime, sort of a typical daytime E region. You sort of have a little bit of an enhancement, but you're at about 10 to the 11 electrons, or 10 to the 5th centimeter cubed electrons. And you can see that during an active night when you have auroral precipitation, you have over almost an order of magnitude increase in the electron density. And as a consequence, if you calculate the Hall and Pedersen conductivities using those formulas we previously showed, you can see that you also get approximately an order of magnitude increase in the peak of the Pedersen conductivity, and also as well in the peak of the Hall conductivity. One thing, just sort of a subtle little point to note, is that the Pedersen conductivity tends to peak higher in altitude than the Hall conductivity. So Hall conductivities are usually lower in altitude and are more sensitive to energetic particle precipitation. So if you have energetic particles precipitating, you might get a stronger enhancement at lower altitudes in the Hall current than in the Pedersen current. And just to show an example as well, I mean, this is an example of various monoenergetic beams. So going from 0.1 keV up to 500 keV, and just showing at what altitudes the ionization peaks occur. So you can clearly, and this is fairly well known, but just to kind of establish the scene here, a 1 keV beam, is approximately 120 or so kilometers, while a 500 keV beam peaks in altitude below 60 kilometers. A 100 keV beam is at about 70 to 75 kilometers. And so this just shows that how different energies of precipitation driven by these auroral phenomena deposit at different altitudes, and then therefore enhance conductivity. And so one way we can derive an actual electron density from this is if we solve the electron continuity equation, not assuming any sort of diffusive processes perpendicular to the magnetic field. We can go ahead and solve this either numerically for the D region, which I have some code that does that, or you can assume the left-hand side here is 0, and you can solve this in the E region, assuming alpha Z, which is the molecular recombination rates. So the upshot is we can get an electron density if we know the ionization profile, which we can get from various models such as the Fang model. So anyway, so I've given a little bit of background here, but I guess the question is, well, so what's actually the problem we're trying to address? And this will lead us into a couple of science questions that will be sort of the focus of this overall presentation. And what I'm showing here is an example of some auroral phenomena and a couple of my colleagues. This was on the night when we launched a rocket. I was actually the PI of that rocket. But so one of the problems is that aurora changes rapidly spatially and temporally. And if you don't believe me, you just watch this video for a little while. And you can see that, there's a lot of changes that can happen on very, very rapid time scales. And so not only that, this is one location located in Poker Flat. And the larger question is, how do we understand this on a more hemispherical? So over the top of the polar cap and over the globe, how do we understand or how do we quantify these spatial and temporal changes? In addition, you can also have significant changes in there's the rocket launch, by the way. You can also have significant changes in magnitude because of rapid changes in the precipitation. So as we showed before, I mean, you can have up to orders of magnitude changes in the magnitudes. And then the final problem that's made conductivity really challenging to study is that there's basically no direct means to observe conductivity. So to my knowledge, there's one observational paper that's been published by Clemens. It's from 1997 that suggested a potential method to observe conductivity, but otherwise pretty much satellites observe either the input flux coming in, which you then have to use models to get to the conductivity, or the ground-based observations from incoherent scatter radar to measure the electron density. But there's no sort of gizmo or doodad that directly measures the conductivity, which is what you'd want. So this is the reason why this has been a particularly challenging topic to study and to actually quantify and get sort of a 4D conductivity profile, like we can with certain other quantities, like electric field, for example. So let me go into a little more detail about some of the specifics about how this is a problem. So what I have plotted here, or what's shown here in this figure on kind of the left-hand side, is kind of an overall perspective in terms of what you need to actually generate a conductivity in the E region of the ionosphere. And basically the way that it works aurorally is you have a flux of particles. We're going to assume for purposes here that these are electrons, although ions can contribute as well. But you have a flux of particles, you have some transport processes, These are characterized by various codes, two-stream codes, kinetic codes. They're transport processes. This causes some kind of ionization. You needed some kind of chemistry model to convert that ionization and capture all the processes that cause recombination to occur. And from that recombination, you get electron density enhancements. Once you know that, you can calculate the conductivity. So this is kind of the basic framework by which you can sort of envision coming down from the top of the atmosphere or the top of the ionosphere and what processes need to happen to actually create a conductivity profile lower down. So part of the problem is that satellites can make good observations of electron density and electron flux. So the input flux coming in, there's detectors for doing that. DMSP has been doing this for a long time. Other satellites as well. So satellites have the advantage of a lot of spatial coverage, but satellites also have the disadvantage of relatively long resample times. So, for example, you have a satellite moving through some auroral region at 8 kilometers per second. The detector itself has a finite amount of time it takes to actually do an energy sweep. So you sort of have some level of smearing effects already happening because of that. But even so, you're basically zipping through something, and then you need to, the aurora is evolving, as you can see from the previous slide, very rapidly. So there is this resample rate problem that you have to deal with. The other major problem is that until we have a dipper mission or some other way to do this, satellites don't directly measure electron density, especially in the E region, just because satellites would deorbit very, very rapidly. So it's hard to get any sort of actual measurement of the E region, at least direct measurement of the E region electron density. There could be other methods that one could use. So I wanted to show at least a couple of examples of some previous models that have been quite successful at specifying conductivity from satellite-based measurements, and perhaps two of the most important ones, especially early on, and I believe this Auroral model is still being used in several models, is lots of using DMSP, and Auroral used the Trio satellite. And from that, you could specify the conductivities as a function of, I believe, Kp in this case. So these models are still used, and these give kind of a hemispherical or overall view of the conductivity. Again, though, one of the issues with these models is that these are statistical averaged models. And so they don't really take into account the real-time variability. So these are, again, our conductance models and used in various current modeling efforts. One of the other more recent advancements has been some of the work that Ryan McGranahan did in kind of almost 10 years ago now. And in this case, Ryan used DMSP observations from various satellites. This just shows the coverage of the DMSP satellites. And from this, he basically constructed an empirical orthogonal function model of conductivity using all this DMSP data and using the GLOW transport code and along with some chemistry to calculate the conductivities. And so from this, the major advancement Ryan made here was that he actually was able to calculate a conductivity profile from this DMSP observations using this empirical orthogonal function analysis. So he's actually able to make a true profile as a function of latitude and MLT. So this just shows an example for the Hall current and then also for the Pedersen current. So flipping this problem I've sort of stated around, the other perspective is you could also use ground-based instruments, and this is the area I've tended to reside in, and the example of the instrument that I'm going to talk about is incoherent scatter radar. So what incoherent scatter radar can do very, very well is actually measure the electron density. So I'm not going to give a lecture on ISR theory, but the most important property incoherent scatter radar can measure is electron density, because that corresponds to the backscattered power that you get from the radar return itself. So in some ways, it's one of the most fundamental parameters it can actually measure. And coding the incoherent scatter radar a particular way, you can actually measure the E region electron density profile. So the other advantage is that ISR can actually dwell under an evolving aurora. So you can watch an aurora evolve. You're basically just sampling sitting under it. One of the issues with incoherent scatter radar that's sort of well known is that in order to apply the incoherent scatter radar theory to actually estimate the ionospheric state parameters, you need to average over a certain period of time. And that has to do with the fact that the model is a statistical model, so it requires a certain number of samples. And basically, there are trade-offs between how long you integrate for versus how much uncertainty you have. So that's one of the trade-offs. So, I mean, there is a certain level of smearing you get from ISR just by virtue of the fact that you can't get around this problem, or at least can't get around it using conventional ISR fitting. So the other issues that ISRs have, the most significant is that ISRs, unlike satellites, don't measure the electron flux directly well. Now, what I'm going to show in this presentation is that there are ways to infer the electron density, the electron flux, but there's no direct observation like you get with a satellite instrument. And the second, more significant problem is that ISRs have very, very constrained spatial coverage. So effectively, you have sort of a ring, an annulus or a ring where you really can sample with incoherent scatter radar, unlike a satellite that has basically, global coverage over the pole. So this sort of is another reason how this complicates this overall problem of why we don't really have a 4D model, because of the differences you have in terms of the observational schemes. And this just shows some early examples of some ISR derived conductances. This is an example from Vickery et al. Using the Chattanooga incoherent scatter radar. For those of you that haven't been to Alaska, Chattanooga is basically at the same place that Poker Flat is now, same town. And then this also shows some data from Brecky et al. 1989, which just shows some IceScat derived results of the Hall and Pedersen conductances during some other storms. So there have been a fair number of past investigations, or a few, but they've still been fairly limited in terms of the number of events and samples that they've actually analyzed. So anyways, I just want to mention a couple of other additional considerations that we have to think about if we're going to try to develop some kind of conductance models, and how we want to specify this. First of all is that, as I mentioned, satellites are able to produce large-scale statistical pictures of conductivities, and ISRs are able to produce electron density profiles over evolving aurora, but again, with the caveat that you really don't understand the input. In both approaches, if you wanted to go, a sort of down or up that ladder over on the left-hand side of the previous figures, you need to transport an ionization model, and both of those require some knowledge of a neutral atmosphere. So, typically people use MSIS. There have been some previous ones used in past studies. And both have distinct advantages and disadvantages, but in reality, we basically don't have 3D 24/7 observations of either electron flux or electron density at high enough spatial resolution to resolve all of the auroral structure. So I want to actually now motivate a couple of, so I've given hopefully a little bit of background about kind of what the problem is, and I want to actually go into a couple of more science questions, and kind of to set up what I'm going to talk about for the remainder of the talk, which is, so the first question is kind of big open question in terms of conductivity, is basically what is the spatial and temporal distribution of aurora, and how does that structuring impact conductivity? So as I mentioned, what we really need is 4D conductivity at high latitude. So 3 spatial dimensions, highly resolved or resolved well enough. And then also the time dimension as well, which is, kind of a can of worms in and of itself about, well, what time resolution is practical versus what can you get. Now, I just want to mention briefly that there's been some work actually in the last few years that have really actually, I think, are motivating tackling this first problem, or at least some great first steps towards tackling this problem. And it's so one piece of work is by Wu et al. This is by Honan Wu, who I believe hopefully is in the audience somewhere. And this is a space weather paper that he published, where he's actually directly assimilating data of electron. This is the energy flux, and then the average energy at 3 different scales. He developed an assimilation technique based off of kriging that he can use this to basically drive the TIE GCM model. So from my perspective, what's shown here is actually some of the first results of somebody actually trying to put realistic auroral structure into an actual GCM model, and from that developing the actual conductivity distribution that you might expect to see. So I think that's a fairly exciting result. The other result is I pulled this from my colleague Christine Gabrielis. So her and Toshi Nishimura have been working on these methods for basically estimating the average energy and energy flux from which you could get the conductivities to actually of all sky images using the Themis all sky imager network. And if you're curious more of the specifics about how they turn white light into filtered imagery, and then from that determine average energy and energy flux, I'd recommend you read or understand what Christine talked about in her paper. In both of these cases, though, I mean, these are really truly first steps towards actually trying to make a 4D picture of conductivity at high latitudes, driven by, actual information. And I think these have both of these techniques together and independently have a very bright future in terms of actually addressing these questions. So the second question that we should address is basically what are the magnitudes of conductivity enhancements driven by auroral particle precipitation? So, it's one thing to get the spatial coverage correctly, but the other half of the problem is you need to get the magnitudes correct in order to be able to, understand how it impacts that high latitude circuit that we see. And so the technique that we're using to address this, or at least one technique you could use to address this, is to actually develop empirical models of conductivity and use which can be used which are accurate or reasonably accurate, and also fast ways to calculate the Hall and Pedersen conductances. So what I'd like to do now is provide just a little bit of historical background that kind of motivates specifically what I did in this study. And then I'll go into talking about some of the methods and results that we ended up using. So the first thing is that empirical models of conductance have actually been around for a fairly long time. To not sound too much too whatever, but I feel like this is one of these things where somebody could stand up in a conference and say we did this all back in the 1980s, and maybe we did. But what I did want to say is that in the early 1980s, there was actually a fair amount of work on this particular problem, and it all kind of started with this figure that was published in this Vickery et al. 1981 paper, which showed. So this is assuming a Maxwellian distribution for the electron flux. They basically ran this through the Rees model and calculated what the conductivity should be. So this is Mo. This is the Pedersen conductivity, the Hall conductivity. And then from that, you could also get the ratio of the Hall to Pedersen conductivity as it changes as a function of average energy. So this provided some baseline sort of figures in terms of what we should expect to see given different auroral inputs. And but I'd imagine back in the 80s, this might have been fairly cumbersome to actually run one of these transport models, especially into larger models. So there was alternative approaches of actually trying to parameterize these curves. And this is where there's been several efforts that attempted to do this. This just shows an example that I found in a Rife review article from the 1980s, but it just shows a couple of different power law parameterizations. So there's sort of this the Vickery relationship, the Wallace and Budzinski, and then a Auroral relationship, showing the ratio of the Pedersen conductivity over the or normalized by the average energy, or normalized by the energy flux, and then a similar relation for the ratio of the Hall conductance to the Pedersen conductance. And then further, this just shows yet another example that came from this, just showing again for monoenergetic beams, showing the Tangle model versus an empirical fit to the Tangle model, which you can see. Tangle was an early transport code model that was based off of Rees. That was probably run by Vickery, basically, because it came out of SRI. So the point with all this is that there was an early effort to try to generate these empirical models that would allow you to very rapidly calculate the Pedersen conductance and the Hall conductance if you were given an average energy and an energy flux. So then we come to the formula of all formulas, or if you'd like to say that, but it's the so-called Robinson formulas. So Robinson in a 1987 paper published these two formulas, which I've shown here, where E here corresponds to the average energy and Q naught here corresponds to the energy flux. But effectively, these two relations that Robinson derived, and here's a comparison of his relation relative to a couple of others, including the Spiro, the Wallace and Budzinski, and then the Vickery paper. One of the other modifications was Robinson did take into account the finite width of energy precipitating, sort of the finite width of detectors in terms of that you go from 10 eV up to 30K EV. So you're not integrating all the way up to infinity. There's a little bit of a correction that you get when you're integrating a Maxwellian. But the upshot of all this is that these have effectively become the de facto relations that are used in several high latitude models in the community, and are also used in various data analysis efforts as well. And so these models, I believe, are ultimately based off the Reese model and then also the Banks 1000K thermosphere. And what I'd like to also point out here is that these are the figures that show the validation of this model. So what's important to note here is that the triangles are the incoherent scatter radar data. And there's all of, I believe, 3 triangles upon which all of this data is being validated against. So this goes to show, and this was the only study, to my knowledge, that sort of rigorously attempted to validate, or semi-rigorously attempted to validate these expressions. So, so the upshot, in my opinion, is that it could use a little more of an examination about how valid actually are these relationships, and are they consistent with sort of observations that you might get, from incoherent scatter radar or other data sources. So the other part of motivating this presentation was that in 2019, or about 2019, 2020, Mike Lamone published a paper or a commentary that basically suggested that the Robinson relations really could use a reboot, and we should consider coming up with a new set of formulas, or at least examining them in more detail. And this paper actually does a pretty nice job laying out some of the background, but there's a lot of interest right now, or at least there's some interest in the community to actually update these formulas, update these empirical relations, and then to further ask the question of how do they actually perform in these high latitude models. So I also just want to mention that I at least have had a bit of a previous contribution to this problem, which is that in 2015, I published a JGR paper where we looked at events, 3 events, basically 2 from the Poker Flat Incoherent Scatter Radar, Pfizer, and the 1 event from the Sonderstrom Incoherent Scatter Radar. And this just shows one of the key figures from the paper. Now, the truth was, this paper was actually supposed to be a little bit of a, I guess you could say, a validation study or a comparison study of some of the work Don Hampton had been doing, estimating average energy and energy flux from scanning Doppler imagers. But what it also turned into was a little bit of a modification of the Robinson formulas. So what I found in this was that effectively the Robinson formula did a pretty good job predicting the Pedersen conductance, but didn't do such a hot job calculating the Hall component of the conductance. And so the old relation that Robinson published was here, and then I created a slight update by basically fitting the data that we had for these 3 events. And then this just shows kind of a new Hall conductance, and you can see that I'm generally agreeing using this new relationship pretty well with the incoherent scatter radar observations. So this was a slight update, but one of the points with this study is that it was still relatively limited. I mean, we studied basically 3 events, and there's a lot more incoherent scatter radar data that spans a whole, lots of events that you'd want to look at to actually try to really come up with a good characterization over a wide range of geomagnetic activity. So what this did is it sort of motivated a better investigation. The first point is that we wanted to incorporate more ISR data to quantify sort of a range of response, so spanning a lot of geomagnetic activity levels, from sort of quiet aurora to very, very active substorms. And specifically, we use data from the Poker Flat Incoherent Scatter Radar, or PFISR, which is located in Alaska right next to the rocket range. The other aspect is we also wanted to correlate all-sky imager aurora morphology to identify the aurora morphology. So the idea was to actually get some context about was what we were seeing associated with diffuse aurora, discrete aurora, pulsating aurora. We used those as sort of the three general categorizations, and didn't go much further into subdividing that. But to understand, like, what sort of conductivity responses do you get as a function of these different auroral types? The third thing was more of a methodological. Basically, in the past study, I used Maxwellians, and I assumed sort of a flux distribution. I assumed it was Maxwellian. For this investigation, we basically relaxed that assumption and didn't make any assumption about the spectral distribution. So we used the FANG 2010 model for monoenergetic beams, and instead of using the FANG model for Maxwellians. But the idea was we wanted to relax those assumptions and try to get the best fit that we could. And the one metric we did use was to get the fit that maximized the entropy, using the method from Semeter and Kamalabadi, which was implemented by a graduate student at the University of Iowa. And I'll get to that in a second. But again, we're using the FANG 2010 model, so a different parameterization for the electron transport. And to give you sort of the upshot, here's the DOI and all that for the paper. There'll be one at the end as well. Okay, so as I mentioned, we have, we're trying to estimate the particle flux. We're given the electron density. We can calculate the conductivity with the standard formulas. So for the chemistry, we used an altitude parameterization for the recombination rate, which is found in Vickery. And then we also have the maximum entropy method, where we're using the Fang et al. 2010 model to calculate the transport and then the ionization. So this just gives an example here of the Fang model. This is what's plotted here is altitude versus energy. So going from 1 keV up to 100 keV, this just shows the sort of the altitude ionization profile. Effectively, this is a matrix that you're looking at right here. So we can write that, basically on the left-hand side, QZ is equal to this matrix times the ionization, or times the electron flux on the left-hand side as a matrix multiplication problem. And then the goal is to basically invert that matrix to produce what the flux would be. So this is effectively your matrix right here. Again, we implemented this using the Fang model, and then the maximum entropy code was provided to me by Riley Troyer at the University of Iowa. He's now at Utah State University, SDL in Albuquerque. But he provided me with some code that helped me with this investigation. So this just shows an example of using the maximum entropy inversion. So the important thing is that the green stars here and the blue line correspond to the actual ISR data. This is just for some interval, or sort of arbitrary interval of time. And then the red is the blue actually. The blue actually corresponds to the fit. I think the blue actually is what corresponds to the actual fit. The dark blue corresponds to the actual fit of the data. And then over here is the actual flux that is consistent with this fit to the data. So this is an example when the fit was, I would consider this to be a very good fit of the ISR data relative to our models. So from the fit here of the electron density, we're able to basically derive the flux. And then once we know the flux, so this is the electron flux in units of meters per, or meters squared per second per, or number per meter squared per second. We can go ahead and integrate this per EV. We can go ahead and integrate this with respect to EV. And from that, we can get the average energy and also the energy flux as well. So this just, again, just shows an example of our inversion methodology. So in terms of the all-sky imager data, so my graduate student, Danielle Markowski, actually did a visual identification of auroral morphology, basically at the zenith point for all sky images. So this was a fairly intensive task for her, where she basically watched a lot of all sky imager videos and basically identified every 3 minutes or so what the sort of dominant auroral morphology was, whether it was diffuse, discrete, or pulsating aurora. along with, whether there was clouds or moon or, other things like that. The other effort was for all this data right here, we refit the Pfizer data, reprocessed it, the alternating code data at 1.5 kilometer range resolution, and including the calibration files. So what this step actually means was I got the raw autocorrelation function level incoherent scatter radar data from SRI. I have a copy of it locally. And then I ran the standard fitting code with some guidance from Roger Varney about how to reprocess the data, including the calibration. So we could basically produce calibrated E-region electron density data. And so we reprocessed all the data from 2012 to 2016 at 3-minute time integration. Just to give some sense about how long that actually took, that took about a week on a multi-core processing machine, like 32 cores. So it wasn't like too onerous in terms of, it didn't take weeks or months or something. It was fairly fast. So that's the data set that we ended up using. So now I'll talk a little bit about the number of events that we had. So after Danielle had done her identification and after I had reprocessed the data and I ran it through the code to estimate average energy flux, produce the conductivities, we basically came out with this is in terms of the number of events. So the total number of events that we had from 2012 to 2016 was about 103,000 events. Of those, 22,000 were categorized as discrete aurora, 65,000, or 6,500 were categorized as diffuse aurora. Pulsating aurora was about 25,000, and unidentified was about 22,000. So just to give, again, the basic categorizations, anything that had structure was discrete aurora. Unstructured glow basically was that wasn't pulsating, so there was no sort of on and off or changing of magnitude, was considered diffuse aurora. Pulsating aurora was structured or non-structured aurora that sort of showed an on and off or increasing, decreasing brightness. And then unidentified aurora was basically light that just passed through the clouds, but you couldn't identify anything. So frankly, it was probably a mix of diffuse, discrete, and pulsating aurora. But since it was through clouds, you couldn't sort of figure out what it actually was. And there are cases when you are in Alaska that you can actually see, a substorm happening overhead, but you just sort of see these bright flashes through the clouds. And then finally, there were out of this data, there were also about 27,000 data points that were considered bad fits. So, and by that, it was sort of some metrics I produced that basically said, I don't believe the data, maybe the electron density was too low. So there's some thresholding that I did to basically consider the events that are categorized here as being acceptable events. So I just want to show an example of, just one example here of some data that we collected. So what's shown here is the actual electron density data from the incoherent scatter radar. This is after doing the inversion and the fitting, this is the modeled electron density. So the upshot is the top two panels should basically agree. This should agree with this. If we did everything correctly, I think we did an all right job in this case. You can sort of see we're capturing the dominant features, the peaks. And then the all sky imager labels here give what type of aurora this was. So DS was discrete aurora. So some of the aurora here was basically discrete aurora. PA was pulsating aurora. So the majority of this showed some sort of on and off pulsation. And then clouds must have rolled in because over here is unidentified aurora or UIA or whatever, just meaning unidentified. With this electron density, as I mentioned, we could also measure or estimate the energy flux. So in this case, 1 up to 50 milliwatts per meter squared, or ergs, depending on if you're into ergs. And then we also estimated the average energy. So in general, this precipitation corresponded to somewhere between 5 and 10 keV precipitation. And then down below, we also calculated the Hall and Pedersen conductances. RR in this case means Robinson relation or Robinson formulas. You can see the difference between that. Pedersen, again, does pretty well, but Hall, you start to see some differences in terms of what Robinson calculated versus what we found from the incoherent scatter radar data. So again, this is just one example out of the, thousands of examples that we ended up, or just one day showing several, data points, hundreds of data points for this particular day or whatever. And so what we could do is we can take all this data and then we can start to actually plot this. So this is the first sort of main result that I wanted to show here. And so what's plotted here are the conductances. So this is the Pedersen conductance and the Hall conductance. So the y-axis here corresponds to the conductance. The x-axis is, in this case, the energy flux in both cases. And then down below, this is the normalized Pedersen conductance, so normalized relative to the energy flux for the Pedersen conductance and then for the Hall conductance. The color coding here indicates what type of aurora it was. You see a lot of blue, which corresponds to pulsating aurora. Red is discrete. Black is diffuse. The lines in the middle here, the black lines, correspond to the 10th median and 90th percentile ranges. And then the dashed curves correspond, and the solid curve, magenta curves correspond to the fit. So I actually did do some fitting to this. I'll talk about that in future slides about exactly how I fit this. But basically the idea was to try to parameterize, to provide some sort of fit so you could sort of rapidly calculate a Pedersen conductance, for example, if you knew the energy flux. And so one other point I want to show here is that the Robinson formulas are shown in red. And so what we can see here is that there is an energy dependence with the Pedersen, but in general, the Robinson formula, especially above about 4 keV average energy, actually does a pretty good job matching our data. Below that, there's a little bit of a difference, but it's, still, I think when I actually calculated some numerical values, it was, off by a mho or two. It wasn't sort of significant. However, for the Hall conductance, we actually see a pretty significant difference in terms of the median values relative to the Robinson formula. So the Robinson formula in this case is actually, the formula here is actually underestimating up to about 10 keV. And then above that, it's sort of okay, but the trend is even a little bit different relative to what we actually saw. So one of the things that we provided in this study was basically updates based on these, 10th median and then 90th percentile levels for various aurora. So just to show a little bit more detail here. So now what I've done is I've subdivided into discrete aurora, diffuse aurora, and pulsating aurora, and this just shows the Pedersen and Hall conductance, and this is all plotted with respect to the energy flux. And so what we've done here in terms of the fits are shown as red lines, either solid or dashed. And we use the basic power law relationship where we have some coefficient A1 and A2 and the exponent A2 are actually fitting relative to the energy flux. And what we find with pretty much all of these fits is that basically the exponent hovers right around 0.5. I mean, it might be 0.4 or something, but it's fairly close to 0.5. And this is actually consistent with the basic theory because basically what you find, this is from Semeter's paper, but it's basically takes the Reese relationship from 1963. And what you can see here is that the altitude resolved ionization rate is basically proportional to the energy flux, which is indicated by phi here. And what I'm calling Q naught, but phi and Q are the same thing in this context. And so you can see that QZ is basically directly proportional to the energy flux. So the ionization rate is directly proportional to the energy flux. And based on the continuity equation, the electron density is basically directly proportional to the square root of the ionization rate, which therefore means it should be proportional to the square root of the energy flux. So the point here is that, the conductivity is linearly proportional to the electron density, which is proportional to the square root of the energy flux. And so therefore this matches pretty consistently with what you would expect. You'd expect to sort of see this square root kind of dependence or this power law of 0.5, 0.5. This is basically all consistent and holding together. Now moving on to, we can also plot the conductance versus average energy. And in this case, what we're plotting here again, we're showing the fits. So the solid line and the dashed line are the fits. This is the Pedersen, where the Pedersen is normalized by the square root of the energy flux. And the reason I did this was basically to isolate sort of the original Robinson formula. So you only have one parameter you're fitting against. Okay, this is sort of your X in this equation where you're trying to estimate all these other parameters. So I did this for both the Pedersen and the Hall conductance. Again, discrete, diffuse, pulsating aurora. Median is shown as the red line, and then the fits are shown for the 90th and then 10th percentiles, respectively. And so I also just want to mention that I did try some other higher order polynomial, just doing a standard higher order polynomial. And it turned out this was the lowest parameter fit that basically did a reasonably good job fitting the data, this functional form right here. So what we find is that we do get, basically what's published as a set of tables are sort of the fit coefficients for these particular models. But one of the interesting things we find is that the pulsating aurora in particular tends to span more of the higher energies, and in particular, especially with the Pedersen conductance. So we can see that, the Pedersen conductance kind of peaks for discrete and diffuse, at about 4 keV, whereas you can go all the way up to, 20 or 30 keV up here for the pulsating aurora. So one of the important contributions is that, the pulsating aurora helps us to understand basically the higher energy contribution and the higher energy tail, at least for how it affects conductivity. So, so anyways, there are slightly different parameterizations and slightly different fits depending on the auroral type is one of the upshots that we found in this study. The final metric that we wanted to look at was the Hall to Pedersen ratio. And this was what this usually is a metric basically of how this scales with respect to average energy. Usually there's a sort of a higher numerical value as you go up in average energy, which is what you can see here. So this is one of the other standard metrics. And what I plotted here, it's a bit of a zoo, but what I plotted here are various other models. So Robinson's model is shown as this bright blue curve right here. You can see that it kind of underestimates the lower energies, kind of at about 10 keV starts to pass into sort of more similar to what we observed. There was also some other models by Spiro, which seems to predict the 90th percentile reasonably well. That's shown by the red dash curve. There's also my older model, which appears to be sort of somewhat consistent up to about 4 keV, and then it kind of diverges off. And then there's a Rife model from 1984, and that's basically completely below everything that we observed at this point in time. So this was one of the other things that we categorized and parameterized. So you might be wondering here, so why is your model that you did, Steve, a few years ago so bad compared to, or so different compared to this most recent result? And the answer is actually the choice of the electron transport model. So shown in the right here is the Fang model. So this was the result that I basically just showed you on the previous slide, or a slight iteration of it. And what's shown here is using the Reese model and producing a similar curve. And what you can see here is that we have the Pfizer. So this was, again, producing the Pfizer data. And what you can see here is that the Kepler model, which is shown as the red line here, does a pretty good job matching the Pfizer data. So remember, with all this, the electron density has not changed in either of these two cases, this case or this case. But what has changed is how you determine the average energy and the energy flux, because I'm using, the Reese model, and I'm using the Fang 2010 model. So I had a nice conversation with Fang at AGU this last year, and he had mentioned that there's some more physics included in that model versus the Reese model, which is fairly simplistic. So I'm tending to, I believe that the Fang model is at least, has more physics included in the parameterization. But the upshot of this slide is that basically it is important what you choose in terms of your model that you're using for the transport. And there are these differences, at least from the very simple Reese model versus the more complicated Fang model. And just to illustrate this, and this is actually my last slide before the conclusions, this just shows an example of the differences that you see. So this is the ionization rate for a 10 keV beam between the Reese model, where you clearly see a higher peak versus the FANG model where it actually peaks at lower altitude. What's more telling here is that the Reese model here for 50 keV shown in black is basically equivalent or has almost the same peak altitude, different magnitude, but about the same peak altitude as the FANG model for 24 keV. So the upshot here is that, sort of from an energy level perspective, and remember that in the previous slide, I'm plotting everything with respect to average energy. There is almost a factor of 2 difference between, what you call 24 keV and Reese is different from what you call 24 keV in the FANG monoenergetic model. So I think this is an important aspect. Hopefully there's some modelers in the community that this is an important thing to consider as models are continuing to be developed and what parameterizations actually go in. Okay, so with that, I give some very brief conclusions, but effectively we derived a data-driven empirical model for auroral conductance. Hopefully I've convinced you that this was hopefully a useful thing to do. We parameterized it based on average energy and energy flux using over 75,000 Pfizer observations with identified auroral morphology. Pulsating aurora has a higher energy dependence relative to discrete and diffuse aurora. If you're interested, this is the location of the publication, or you can look up my last name. And 2023. I would say the most important part is actually the tables in the paper. That actually gives the actual parameterizations and the fits. So if you use that, just as a side note, again, I just want to thank everybody. If you do end up using this new parameterization, I would be interested to know how well it performs. And if it provides any kind of improvement. I don't expect it to be a fix-all, but I hope it's at least a step towards better model data agreement. So with that being said, thank you again.
Thank you. Does anyone have any questions either in the room or online? If you're online, you can either raise your hand or type into the chat. So Lian, go ahead.
Yeah, so Stephen, so I would like to know, this empirical model, does it only consider the electron precipitation, or does it also including proton ion precipitation?
So we have to assume with Pfizer that I'm assuming with Pfizer that what we're seeing is the electron precipitation. There's, to my knowledge, no way to distinguish the two from an incoherent scatter radar observation. So
Okay.
that was just an assumption we made in the paper.
Okay, so basically it's a electron precipitation between like 0 to 30 keV range.
Yeah.
Okay, all right. Okay, thanks.
All right, thank you. Other questions?
Yeah, hi Steve. Nice talk. How do you deal with the neutral atmosphere in your derivation?
So we used so the neutral atmosphere comes into play when we're running the FANG model. You have to run MSIS at some, or we ran MSIS, and it ran MSIS 2000, so it wasn't MSIS 2. And you need to use that to actually do the calculations of the various, I'm going to say the various formulas, but there's sort of a set of 4 or 5 formulas, and you need to put the neutral mass density in there. So that was the first step. The other step was we used MSIS for calculating the conductivity profiles, the ion neutral collision frequencies, which went into the conductivities. So those were the two main areas that we used MSIS. I'm not doing anything otherwise than that for the neutral atmosphere. And I mean, one thought I've actually had is that if there was other neutral atmosphere models, it would be interesting to see how much that might change the overall results. So something that somebody runs, I actually, that's something I've thought about doing. I just haven't done it yet, but I'd be happy to work with people on that.
Yeah, great to hear that. Actually, that's what I'm planning to do in a recent proposal. So MSIS, I know that's very easy to use and widely used in, for example, ISR data processing. So what I'm about to do is using the PyTCM model so that we can get a more dynamic variation, especially during storm time. And I'm going to see like how that neutral background variation would impact results on conductivity and conductance. Yeah, thanks for sharing that.
Yeah, and sure, I'd be happy to talk, or I'd be interested to hear what you get too. I mean, that's actually sounds very useful.
Yeah, sorry. In particular, the one of the motivations is that we found the MCs kind of underestimated the neutral density, especially during storm time, compared to observation or some physics-based models. So that's one of the big motivations for doing that.
Well, that sounds good. Yeah, no, that sounds really neat.
Bill, I think you have a question.
Well, I kind of did, but Dong kind of already went there. But my question, I realized that trying to get conductivity from a dynamic GCM rather than EMSIS, it wasn't part of your study, but just to take Dong's thread a little bit further, do you have any thoughts about that? Have you looked at how well or different, it's really how different empirical models are in specifying conductivity versus what comes out of a GCM of some kind?
So the short answer is no, but the longer answer is Shen Liu is here, and I should really or a slightly longer answer. Shen Liu is here, and I know that she, has and Honan. Hopefully many of you know Honan by now, but I mean he was her graduate student. I think they've got a lot of GCM model run, and I mean, it actually would be a good investigation to see how much change I get in terms of some of these specifications as a function of thermospheric model. What I can say is, I think a lot of the reason why in the 2015 study, I sort of mentioned this, and then I mentioned it again in the more recent one. So there was I think a lot of the reason you're getting a difference is because of the Banks 1000K model that Robinson used versus I used EMSIS in at least the 2015 paper. And I attributed that to being probably one of the contributing factors to why the Hall conductance was different, because the Hall conductance is more dependent upon the penetration of the electrons. So, so how they penetrate and how deep they penetrate is going to be more of a function of the neutral mass density, which could be different between these two models. So I do suspect there would be some strong impacts, or and it'd be good to quantify that. The other comment I'll make is that there's a Watson paper, space weather paper, I think it's by Watson, where they actually did do a little bit of investigated some of the variation that they saw in conductivity. So it was a Guvi Suzy study. They also used incoherent scatter radar. It's a space weather paper. But they did at least gave some sort of estimates for kind of range of variability you might expect, and which ones contribute the most to, I forget exactly what they were looking at, but they did at least try some of that a little bit. It's sort of a points in the right direction of what you might want to try.
Yeah, well, that's good. Thanks for taking that as far as you could, given where you are right now. But so yeah, I think that's really the thing that we need to do is to understand. I know that we have a dynamic thermosphere and how much that's impacting the fourth dimension in your 4-bar model. So anyway, thank you. I enjoyed your talk.
All right, thank you.
May I ask another question? So I think another important factor in calculating conductivity is the spectrum shape. So remember in your 2015 paper, you mentioned how that matters, and also, but seems like in your most recent one, the 2023 paper, you're not relying on any pre-assumed function shape for that, right?
That's right. So I think I used 25 monoenergetic beams distributed between 1 keV up to 100 keV. And the maximum entropy method, so this method that Semeter and Kamal-Labadi came up with, basically the point was you estimate, or you find the profile that basically maximizes the entropy, and that entropy maximization is like the metric by which you say, I think this is the right profile, or this is the one that's most consistent with the interpretation of maximum entropy, which I know has stuff to do with the information content. I know I'm giving a little bit of a hand wavy answer, but it's sort of I forget, like the minimum amount of information. It's like, given the way the data works, it's like the minimum information solution, or like is one way to put it. I'm not answering that very well, but effectively the one that we're choosing is the one that maximizes the entropy as the answer.
Yeah, I think it's great to see you have already tested this. I guess the fundamental prerequisite is that you are implementing the FUN method, which we are going to implement in the TIDCM as well, with the precipitation we get from the magnetosphere model. So yeah, we'll see how similar different the results will be.
Yeah, I mean, it'd be interesting to try to validate some, like for particular case studies, try to validate some of this against Pfizer observations too, or you know, like, well, it would be great if you could input Pfizer and then validate that you get Pfizer out, if that makes sense. Assuming, you know, like the electron density going in, you've inverted it, and you know, like one of those loops sort of things. So, are there other questions?
Well, I'll just ask one other thing. Ovation Prime. So, you know, in the Ovation Prime model, pulsating aurora is not specifically one of the populations. And I've thought, I'd like to sort of validate this with your thinking, that in part because DMSP doesn't go to as high energies as pulsating aurora exhibits, that some of the at least the lower energy stuff in pulsating aurora is probably just mixed in with what Newell called diffuse aurora. Is that
I think that's generally consistent. I mean, I think my understanding is that I think there's been a little bit of a lumping pulsating with diffuse, is the way I've understood with conversations I've had with some other colleagues, that it's been more like people just kind of lump pulsating with diffuse aurora, and so therefore it's diffuse, and it's not discrete because it's not a parallel electric field at high altitude is
right.
the, you know, the monoenergetic. That's the basic thing. I mean, the other issue you might run into with DMSP in particular is just that you might be sampling through the region so fast that diffuse and pulsating might sort of look the same.
Yeah.
You know, in terms of a spectral characteristic, you'd see it's not like an inverted V or something like that.
Right. Okay. Well, it's good to hear somebody's thinking that's similar to what I thought. So that's good. Thanks.
All right. Thank you.
Okay, so I don't see any more questions. So thank you again for nice talk. I think everyone enjoyed it.
All right. Well,